Okay. Hi, everyone. So as promised, I want to spend a few moments going over the final project and what you will be doing. I know a few of you have already kind of gone through and had your selections for your topics. So I know a few of you have actually read through this document, but really quickly, what you'll be doing for the final project is looking at some of the already existing climate change solutions and presenting that information, summarizing it in a media format of your choosing. So I've outlined a few. You could do a recorded presentation or a podcast where you like summarize these different solutions, an informational flyer or brochure, maybe even a social media deck. Like imagine you're trying to sell this solution to Irvine City Council or to UCI to implement. Like how would you go about doing that? What media would you use, right? So if you have another idea for the media format that you'd be interested in doing, just check with me first and let me know if, and I'll let you know if I think it's something that is good because we have to be able to have them uploaded to the Canvas page for you all to look at later. Okay, and so what I mean by some of those solutions, let's just go here to the file that I have uploaded, your final project, right? So Project Drawdown is this nonprofit organization that helps to seek drawdown, the point where our greenhouse gases in the atmosphere stop climbing and actually start to decline. And they have a really well laid out library of solutions here. Okay, so you can click on any of these and read more about them, and they kind of go into some detail, like obviously like electric cars. What is an electric car? What would the impact be? How much does it cost to implement these solutions, right? And so there's a lot of information here to get you started. There's also more references if you want to dive deeper, learn more, right? If you're, one of the things you'll be doing is looking at whether the solution is already implemented in the local, state, national, or global level, right? So local could even be just UCI. Is UCI doing something of that nature, like EV vehicles? Maybe they have EV charging stations. What's the state policy? What's the state doing, right? So you'll have to do a little bit more research than just what the Project Drawdown website has to offer. But it shouldn't be, you don't need to write like a full research paper, right? Here is your presentation rubric, how I'm going to grade you, right? Making sure that you go through each of two of those two of those solutions and including this information that's listed. Okay, and once you decide which two solutions you want to do your research on, you need to go to this Google document, which is an Excel spreadsheet here, and add your name as a comment. And the reason I did this is just if everybody had access, then people could accidentally start deleting things. So you'll have to come in and add a comment with your name on the solutions that you would like to do. And I will come through every few days and update it with your name. That being said, right now there's 53 of you enrolled in the class, and there's only 96 solutions. So if each person does two, that's a few solutions short, but I'm not sure how many people will stay in the class. So if there gets to the point where we have to duplicate a few of them, we will do that. But we will see, it's just a natural thing that some people will end up dropping the class after the first week. But go ahead and pick your solutions. And in terms of due dates, please have your topics picked, which solutions you would like to do by next week, the 17th. And what you're going to do is you're going to upload your presentation in whatever format you decided. If you're doing a recorded PowerPoint presentation or a podcast, you need to upload those files to the discussion forum, which I'm going to open. I haven't done all that yet, but it will be available by September 12th. So that's half of your grade is doing the research. And then the other half of your grade is going to be looking and engaging some of your peers' presentations. Now, you're not going to look at everyone's presentation. That's way too many. I would never ask you to look at 48 plus presentations. I will assign you a number and I'll assign you which presentations to look at so everybody gets some feedback. And that's the other half of your final project grade. And that will be done asynchronously. So I will give you basically 2 days to do that. So the presentations are due September 12th. on September 12th, you can look at the presentations, or you can do it September 13th. You have 2 days to do it. I'm not going to say you need to do it at a certain time. It'll be asynchronously. You just submit your file showing that you've looked at each other's presentations, and that's it. Okay, so if you have any questions about that, just let me know. I'm happy to answer any of that. But just reminder, it's only 5 weeks. We're already at the end of the first week nearly, so it's going to come fast. So don't put this off to the end. Start looking at your solutions now. Are there any questions right now? Okay. So that's that. I also wanted to let you know that I created a Discord server or channel. I'm not sure what the terminology is because I'm a Slack person. I've only ever really used Slack, but last session, the students at least seem to find it helpful. You can get in touch with me a little bit quicker than email if you have any questions. So I'm just going to, oops, get out of this, copy this. I'll put it in chat here. This is also on our Canvas page. On the home page, you'll see that it says the course Discord channel. Feel free to sign in there if you'd like. You can ask me questions, but we want to abide by academic honesty. So, don't use it to cheat or share answers on the quizzes or anything like that. Okay, but a resource for asking for help. The next thing I want to address is where the lecture notes and recordings are. So I don't know if I did this, but I just wanted to show you here. So let me go to student view because I see much more than you all do on my Canvas. So here on the left under files, you will find lecture notes. That's where I will put the PDFs of the lecture notes. So today's lecture notes are here as well. You can download them and have them for your note taking and and whatever purposes you'd like them for. And then in terms of the lecture recordings, those are going to be under pages. Okay, so under pages, you'll see lecture recordings. You can click on that, and I will upload a UJA file for you, typically by the end of that day. Okay. Yeah, so that's all I wanted to say there. So those are some logistics. And then in terms of like thinking about climate change right now, okay, so a very tragic, unfortunate circumstance in Hawaii. At least 36 people have died as this wildfire has ripped through Maui, destroying, the town center, which was, several hundred years old with lots of history, cultural history, and it's really, really tragic. And I just want to say, maybe a few of you watched some of the video I posted regarding this news event. A lot of this is fueled by increased, extreme weather and the very fast winds due to a hurricane off the coast of Hawaii. So it's really, really tragic. And so when we think about climate change, it is happening now, and it's a sad reality. And what's really even more terrifying is, on an island nation like Hawaii, or an island state, or just in any type of whatever whatever you want to call these locations, these island communities, they are very much at risk, because right now, how do they get help? How do they evacuate, right? Some people were going into the ocean in order to get out of the wildfires way. So it's really traumatizing. I can't even imagine what these folks are going through. So we're going to keep them in our thoughts as we talk today about our greenhouse effect. Okay, so let's take 2 minutes and look at this figure. This is again from our Intergovernmental Panel on Climate Change, showing some information. So I want you to spend 2 minutes, type up, what does this figure show, and what conclusions can we draw from it? And you can put your answers into chat when you are ready. Okay, great. Yes, reading through some of your responses, and that's right? So this figure is showing us with a color scale some information about observed change in annual precipitation over land, right? So if we look at the two panels on the left, this is showing us the change from 1901 to 2010, and then just the 1950 to 2010, so the more recent periods. The darker browns and the tans show us a decrease in precipitation in terms of millimeters per year per decade. And then the blues and the darker blues are an increase, right? So one of you said it really well, is that the locations that were already experiencing more dryness or less rain to begin with, in the more recent years are seeing even more of that extreme. So kind of that polarization. Someone also said polarization of the the weather or the precipitation. So the wetter places get wetter and the drier places get drier. And that's one of the main conclusions from the IPCC, is that when we think about precipitation extremes, we will see this, that places that are already wet will stay wet, get wetter, have more flooding issues, and the places that are dry will stay dry and have more drought issues. Okay, great job. So today we're going to talk about our atmosphere, what's going on in the atmosphere. We're talking about our greenhouse effect and how that greenhouse effect actually helps to make Earth habitable. And then we'll talk about how our energy on Earth is transferred and how that heat transfer helps to fuel our atmospheric circulations. Okay, so just remember from Tuesday, the main difference in the radiation between the sun and the Earth is due to the temperature of those objects. The sun is much hotter, and therefore it's going to emit more radiation in a shorter wavelength or short wave. And the Earth is cooler, and therefore it will emit more of its radiation in a longer wavelength, or what we call long wave radiation. And the difference between those is going to matter when we talk about our greenhouse gases. Okay, so how much how much of sun's energy does Earth receive? Well, we can do all these calculations. Think about the fact that the sun is a sphere emitting energy in all directions out, and the distance you are from that sun will determine how much of that energy you intercept. And so that is our solar constant. It is calculated simply from the luminosity or the energy given off by the sun and the area of the sphere, with the radius of that area of sphere being our distance from the sun. So you can calculate a solar constant for any planet, really in any solar system, as long as you know the star or the sun's luminosity and your distance from that star. And we talked about our mechanics, right? Earth has a revolution around the sun that defines our year. We have a rotation that defines our day. And then we also have the fact that Earth is tilted. And that tilt is the principal cause of our seasons. And because of that tilt, it impacts the amount of solar energy different latitudes receive, impacting our length of day, as well as that solar angle and beam spreading, how much energy gets kind of spread out over a larger area. So then it's a little bit diluted or dispersed. So it's not as strong. You're not going to get as much heating if you're taking the same amount of energy and spreading it over a larger region. We talked about Earth's albedo, right? This reflectivity, how reflective are our different Earth surfaces. And when we look at Earth, we can see that there are many different surfaces of different color. Really, it's the color that's going to help with this reflectivity. When we average all of our surfaces together, Earth's average albedo right now is about 0.3 or 30%, meaning 30% of the incoming sunlight we receive gets reflected back to space and therefore does not contribute to the temperature we feel on Earth's surface. Okay, and we also mentioned that albedo changes. It's changing hourly, even less than that really, because of clouds, daily, seasonally, and of course, over the last few decades due to climate change and changes in snow cover and ice sheets and glaciers, and other things like land use change. Deforestation, for example, will change the albedo. And we introduced one of these climate feedbacks, right? When we think about our feedback loops, we want to think about the components, our two boxes here, and how they are interacting. How are they coupled, right? So we said if we start with an increase in surface temperature, that would decrease the amount of ice on Earth, which means those two components aren't negatively coupled. They do not have the same change. One is an increase and one is a decrease. And if we decrease the amount of ice on Earth, that will also decrease Earth's albedo. And those two components have the same change, so that's a positive coupling. And then if we decrease Earth's albedo, that's going to have the effect of increasing Earth's surface temperature because we're going to reflect less of that incoming sunlight back. Okay, and so this would be a negative coupling between the two components. But when we think about the whole loop, we end on the left here with an increase, and we started on the right with an increase, which means this is a positive feedback loop. It continues or it amplifies, and the change that you start with will be the change like that you end with. It keeps going. And so positive feedback loops are not always great when we think about changes in climate because it makes it hard to stop these amplifications. Okay, so this is where we are. What controls the planet's temperature today? We're going to get into the greenhouse effect and our absorption and scattering idea. So what is Earth's temperature? What is the temperature that Earth is radiating, right? We can figure out, and we know that Earth radiates energy in the form of long wavelengths. And that's because of the temperature. What is Earth's temperature? And you can calculate the radiative temperature of any object or any planet, for example, if you know how much incoming sunlight it gets and you know its albedo. Okay, how much is it reflecting? Okay, so this equation, it looks a little intimidating, but it's really not, right? We have a few things that we're familiar with already. We have the sigma constant, which is the Stefan Boltzmann constant. We already saw that before. We have T, which is the temperature of the planet raised to the fourth power. And then we have S, which is our solar constant, which we know is just based on the luminosity of our sun divided by our distance or area of the sphere. And then 1 minus A. A is the albedo of the planet. And with that information, we can calculate our temperature. Okay, and so what is Earth's radiative temperature? Well, we can calculate that. Okay, so let's do it together. So we have sigma T e to the fourth equals S over 4, 1 minus A. And I'm going to pause right here and tell you this is going to show up on your homework. Okay, we're going to do this for other planets. Now, I personally like to solve for my variable first before I put in my numbers. So I'm going to do that now. I want TE by itself. So to get TE by itself, I'm going to divide both sides by that sigma. Okay, and then because I have that fourth power, in order to remove a fourth power or an exponent, you have to raise it to the fraction. So I'd raise it to 1 over 4 because when you have exponents next to each other like this, they multiply out. So 4 times 1 over 4 is 1. But I have to do the same thing to both sides. And so I'm going to have something that looks like this. So now I can actually just have T equals S in this case is my solar constant, which we know is 1370 watts per meter squared, divided by 4. 1 minus our albedo in decimal form, which would be 0.3 over 5.67 times 10 to the minus 8 watts meter squared Kelvin fourth. And this whole thing will be raised to the 1/4 power. And so the main thing here that you might get hung up on is your order of operations and having the right brackets, right? Thinking of making sure all of these numbers get in the right order of operations on your calculator. All right, so I'm going to pull up my Google calculator, and I think I can do this in Google Calculator. I've done it before. I just have to keep track of my parentheses. All right, so I'm going to do this move so I can see what I'm doing here. We're going to have 1370 divided by 4 times 1 minus 0.3, that whole thing divided by, oops, yeah, this should work, divided by 5.67 times 10 to the minus 8. Where's 8? Minus 8. And then we're going to raise that whole thing to the 1 divided by 4. There we go. And so I get a number that is 255. And if we look at our units here in our equation, we get T equals about 255. Now our units here, we have watts, and the watts are canceling out, and the meters are canceling out, and then the fourth cancels. So our unit is Kelvin. Okay, and Kelvin is a temperature scale. And that also makes sense because I'm solving for temperature. Okay, so Earth's radiative temperature, based on this equation, is 255 Kelvin. Well, I personally don't live in Kelvin world, so I'm gonna ask my friend Google to help me convert that to a number that I might better understand. Okay, so I'm gonna go to Google here, and I'm gonna say 255 Kelvin to Celsius. Okay, 255 Kelvin to Celsius. I even tell you the formula is you subtract 273 from the Kelvin value to get Celsius. So we get minus 18 degrees Celsius. Okay, minus 18 degrees Celsius. Does that number seem reasonable to you? That Earth's temperature, average temperature, is minus 18 degrees Celsius. Seems a bit cold, okay? Yeah. Okay, so hold on, let me go back. Again, maybe you don't live in Celsius world. In America, we don't because we're interesting. The rest of the world does use Celsius. So let's use Google again. Let's do minus 18 C to F. That is right at minus 0.4. So like minus degrees Fahrenheit. Very cold. Okay. Why? Yeah, it doesn't seem right. Because that would mean there are places well below that temperature. And that would mean that most of the water on our planet would be frozen because it's below freezing point, which is 0 Celsius or 32 degrees Fahrenheit. So why is Earth not permanently frozen? What is this equation not accounting for on Earth? Well, we did account for the sun in the solar constant, right? This, we know how much energy we're getting. The atmosphere. This equation has no idea whether or not our planet has an atmosphere and what is in that atmosphere and if that atmosphere helps to heat the planet. All right, so our atmosphere, okay? The atmosphere, we call it air. It's a thin layer of gas and it's retained by Earth's gravity and it surrounds our planet. And I love this image from NASA. You can see it's just a very thin envelope around our planet. And when you compare it to the actual size of Earth, how deep Earth gets all the way into the core, the atmosphere is just like tiny, tiny bit. Okay, so thin. But it's a critical component in making our planet habitable. Now, what is the main gas in our atmosphere? What gas makes up most of the air we're breathing? Is it oxygen, nitrogen, water vapor, argon, or carbon dioxide? All right. So the answer is, in fact, nitrogen. Okay. So every time you take a breath, 78% of that breath is nitrogen and about 21% is oxygen. And the remaining 1% is gas like argon or water vapor, carbon dioxide, all of those combined is about 1%. The amount of oxygen and nitrogen in our atmosphere is pretty stable through the last several billion years, really. Um, Oxygen can vary based on photosynthesis. And we don't want too much oxygen in our atmosphere because it's flammable or combustible. And so you would have a lot of fire. So that 21% is a really good number to have right now. Okay. So those little bits of gases in that 1% are actually going to be really important in determining our actual planetary temperature. Okay, and our atmosphere has many layers to it, and we're going to talk about those in detail, but we have our troposphere, where we live, where weather happens, where airplanes fly. We have our stratosphere, which is a bit higher. We can have some weather balloons, some information can go up to the stratosphere. And for this class, really the only two levels or layers we care about are the troposphere and the stratosphere. Okay, and when we look at some of our atmospheric properties, for example, air pressure, the force per area that the air pushes or exerts on us at the surface, and the density, the molecules, how close or far away they are, both of those decrease exponentially with height. So we can see here, here's our altitude going from 0 up to 500 kilometers. And we can see that those decrease quickly. The main reason for that is gravity, right? Gravity is keeping that air, those gases, closer to the surface. And so as soon as you move further away, you start to decrease the pressure because there's less molecules above your head. And of course, the density will decrease too because, again, less molecules per the same area. So gravity is important for keeping a lot of our atmosphere towards the surface where we are, which is good because we like to breathe and we don't want to breathe too we don't want to breathe we don't want to be challenged to breathe is what I'm trying to say as I live at 5,200 feet elevation. So there's less air here. Our density of our air molecules is less, which may be why I'm having trouble thinking today. Okay, so let's try this out, and I hope this works. But at the top of your screen or at the bottom of your screen on your bar, your Zoom bar, you should be able to see a button that says annotate. Looks like a pen or pencil. And on the screen here, you should be able to, once you click on annotate, use it to draw. Okay, and what I want you to do is I want you to think about how temperature can change with height in our atmosphere. Okay, so on the X, we have temperature with an arrow pointing to the right. So on the right of our graphs, that would be warmer. On the left would be cooler. And as we go up and down, okay? So see if you can draw what you think temperature looks like with height in our atmosphere. To annotate on your Zoom bar, your menu bar, there should be an option that says annotate. If it's not showing up, you might have to click the 3 ... dots for more, and it might be there. And I'm not sure if you're using a certain device, if you're on a phone or a tablet, I don't know if that's going to show up. And also sometimes, yeah, sometimes it depends on what version of Zoom you're in. So it's, again, you're not getting any like credit for this. It's just an activity to see what people draw. So I apologize. Okay, green pencil above the mute button, maybe for some, or a pen icon. All right. Well, thank you though for those of you who tried that out. And there we go. Thank you for all helping each other there. Okay, so a lot of you are drawing temperature decreasing rather linearly, I would say, or mostly linearly, or kind of exponentially, okay? So I'm going to tell you now, so I'm going to clear all that off, sorry, just so we can move on here. That temperature does not change uniformly in our atmosphere. And why is that? So let's take a moment to think about how our atmosphere is heated. Okay, what do you think? Is our atmosphere heated through radiation? Is it heated through convection, warm air rising, cold air sinking, or is it heated through conduction? All right, so we're a bit split between convection and radiation. And I'll tell you, it depends on where you are in the atmosphere. So the way our atmosphere is heated is mainly by the sun heating the ground itself, heating the soil, heating the land via radiation. Okay, sun's rays coming through the atmosphere, those rays, electromagnetic shortwave energy, will heat up the ground. Okay, it doesn't actually heat up the air via radiation because air is not that great of a conductor of heat, surprisingly. So it's not the sun heating the air itself, it's the sun heating the Earth's surface. And then the ground is in contact with a very little bit of air, and that air gets heated via conduction from the heat of the ground. Then that air rises because it is warmer and less dense, and warm stuff rises. And so the atmosphere really is heated during the day via convection. Okay, so the warm air rises. So during the morning hours, the ground is heating up. That thin layer of air that's in direct contact with the ground heats up, rises, and then cooler, colder air comes in beneath it, and then that air will get heated and rise. So during the day, we get convection. Okay, so all three of these are important for heating our atmosphere, but radiation itself is not solely responsible. In fact, it's not doing what we think it's doing. It's heating only the Earth's surface. Okay? And so when we look at the atmospheric temperature, it's not a straight line. It's actually zigzaggy. And that's because in the troposphere at the bottom where we live, we know that the surface is heated by conduction. And so it's warmest near the Earth's surface. And as you move higher in the troposphere, away from the surface, it gets colder. So temperature decreases with height in our troposphere. That explains why you can have snow on mountains, right? As you go higher up in elevation or altitude, air temperature drops. Okay, and that's why if you've ever been on an airplane and you watch the little in-flight screen and it tells you what the outside air temperature is, it's usually like minus 20 degrees or 30 degrees outside because your plane is flying way up here, right near the tropopause. Quite cold out there. Okay, and then in the stratosphere, the layer above our troposphere, the temperature actually increases with height. It's doing the opposite because of a gas known as ozone. Okay, ozone, you may have heard of it, is really good for us in the stratosphere because it can protect us from the shorter wavelength energy from the sun, that ultraviolet radiation that can cause skin cancer, sunburn, cataracts, tissue damage. And when that ozone absorbs that shortwave UV energy, it heats up. And so that's why the stratosphere actually gets warmer with height. Our mesosphere gets colder, and then our thermosphere gets hotter. Okay, but again, for this class, we're focusing on the troposphere and the stratosphere. So troposphere gets cooler with height, and the stratosphere gets warmer with height. So that's going to lead us to our greenhouse effect. Okay, and if you've ever been in a greenhouse, you know they're warm. Okay, and that's kind of the point, right? We want to be able to grow plants, vegetables, fruits, whatever it may be, in a place that maybe doesn't have the climate for it. And so a greenhouse can kind of keep a more controlled and warm environment. And the way this works is that we know the sun's energy is in the form of short wavelength, the majority of it. Okay, those shorter wavelengths can transmit through the glass of the greenhouse, no problem. They just go right through. And that heat, that radiation, will heat up the ground. The ground heats up the air inside. You start to get some convection, warmer air rising, cooler air sinking. Now, the ground and the air inside is not the same temperature as the sun. Okay, it's going to be very much cooler, and therefore it will be more of a longer wavelength, the heat, the temperature, right? Everything emits radiation. So these plants are emitting radiation, the ground, the tables, because they're heat, they have energy. And so the wavelength of energy that they're releasing is going to be in longer wavelengths. Okay, and the reason, I should pause here, the reason everything emits radiation is that it's absorbing radiation, right? You and I are constantly emitting heat. Otherwise, we would burn up, right? The Earth is doing the same. It's getting sunlight, getting heat, it heats up and sends some of that heat away. And that's what we call an energy balance. And so in our greenhouse, we got the sun short waves coming in, heating up the ground and the plants, and then those which are cooler in temperature, lower temperature, will emit more long wave. But some of that long wave radiation cannot pass through the glass because the glass is what we call a selective absorber of longer wavelength energy. And so some of that energy gets trapped by the glass and gets sent back to the ground. And so now the ground is getting extra heat from the energy that was trying to be released from the greenhouse via the plants and whatnot. And this is the greenhouse effect on our planet. And Earth is always giving off heat, okay, in the form of infrared energy. And we can use that infrared energy and that heat signature to actually look at the Earth's surface via satellite. So we can look at those wavelengths. So I'll look at that really quickly here. If we look at some of our satellites, this satellite, if you see color like browns and greens, this is what we call a visible satellite. It's basically a camera just looking down at Earth's surface. Okay, so it's what you could see. You could only see the Earth during the day or in the sunlit portion. You don't see a visible signature at night. But if we go down here into some of our near infrared or infrared, you'll see that we don't see color, we see lights and darks. And this is the heat or the lack of heat. So these whites are clouds and they're cooler. And so they're showing up as a different infrared signature to these satellite cameras. Okay, so Earth is giving off mainly infrared energy. And so the greenhouse effect is that some of our atmospheric gases are very poor or bad absorbers of shortwave energy. Okay, so our sun, remember, is shortwave, visible light, it's just coming into the Earth's surface. The atmosphere, those gases just don't know. They just don't care. Their chemistry, their molecular structures, they don't care about shortwave energy. But some of them, those greenhouse gases, are really good absorbers of long wave energy. That infrared radiation the Earth is trying to send back to space so it doesn't get too hot. And some of those gases are carbon dioxide, CO2, methane, CH4, and surprisingly, water vapor. Okay, water vapor is actually the most potent, I guess you could say, greenhouse gas, but it is has a very short residence time, meaning it goes and comes really fast, right? We can have storms and it moves away, whereas CO2 and methane are much longer lived compounds. They exist for a lot longer in our atmosphere. And the big thing here is that when those greenhouse gases absorb that long wave energy, that long wave radiation, they heat up, just like the Earth does when it receives shortwave. Those gases will heat up, they have a temperature, and therefore they will emit radiation themselves based on their temperature. And so they will absorb and re-radiate heat, mainly in infrared or long wavelength, back to the Earth's surface. And so the Earth is getting a double whammy here. It's getting some of the sunlight from the sun, heat from the sun, and it gets some of that extra heat that the greenhouse effect, those greenhouse gases, are sending back to Earth's surface. Okay, and so just a little vocabulary here. Transmission, if we say something's transmitted through the atmosphere, it means it moves without impact. There's nothing happening to it. The atmosphere doesn't care, just transmitted. Absorption means it gets absorbed. The energy gets absorbed by the atmosphere. Okay, and so our greenhouse gases, as I mentioned, are selective absorbers, right? So here's our CO2 carbon dioxide molecule as that sunlight, that shortwave radiation just can transmit through. Those molecular bonds are not impacted by that shortwave energy, but they love infrared energy. Okay, so they're going to start to absorb that heat and heat up and then re-emit that energy back to Earth. And that is important because without some of those greenhouse gases in our atmosphere, Earth would be very cold. We just calculated that temperature as minus 18 degrees Celsius. So I want to emphasize that the greenhouse effect is not inherently bad. Okay, so when people say, oh, the greenhouse effect, actually, without some level of greenhouse gases in our atmosphere, Earth would not be habitable. It'd be too cold. The main issue is that we are taking something in a natural state, right? We have a balance. We had a set amount of CO2, those greenhouse gases, and now we're adding too much. If you're adding too much, then it's going to get hotter. But we'll pause there, and I want to look at this graph that shows some of the absorption spectrums. So what wavelengths of radiation do our different gases in our atmosphere absorb, and which ones do they transmit? So each line here is a different gas. So on the top, we have methane, nitrous oxide, oxygen and ozone, carbon dioxide, water vapor, and then when you sum, you add all those curves together, the pink, purple bottom one is the whole atmosphere together. Okay? On the left here, we have infrared. So these are those longer wavelengths. In the middle is visible light. And on the right is ultraviolet, shorter wavelength. Okay? And you can also see the wavelength numbers down at the bottom. I'll just write short, shorter on top, and longer here on the left. And what we can see is that these gases like to absorb certain wavelengths of energy. Methane does not absorb visible sunlight. It doesn't absorb UV sunlight, or sorry, UV light or energy. Same with nitrous oxide. They're absorbing mostly and only in the infrared. But the infrared is the energy Earth is sending back to space or trying to send to space. Okay, oxygen and ozone, it's a different story though. I just mentioned ozone, right? O3, it is absorbing UV, which is good. Okay, for us. Carbon dioxide, again, really only absorbing infrared. And then here's that water vapor. Water vapor does a lot of absorption in many different wavelengths. And when we look at the whole atmosphere, so just focus here on the bottom now, you can see that we have what we call atmospheric windows or areas of wavelengths that the atmosphere does not absorb in. And we actually use these wavelengths to look at Earth, right? Because if we're trying to send a satellite or like use a camera at a wavelength that the atmosphere absorbs in, it's going to absorb our infrared detector image, right, from the satellite. So we send signals to Earth at different wavelengths. And we also can see that our visible wavelengths here, our atmosphere does not really absorb, which is good for life on Earth because we've adapted to having visible light. We can see visible light. So we don't want to absorb it. If our atmosphere absorbed visible light, that would not be good. Okay? So that's our infrared. Anything on the left here, absorbing infrared, is what we would call a greenhouse gas. It's going to selectively absorb the longer wavelengths and transmit the shorter wavelengths. All right. So again, looking at the same graph here, which gases absorb part of our incoming solar radiation? We also call that insolation. What wavelength is our incoming solar radiation? Alrighty. So here we go. Now remember, we're looking at incoming solar radiation or insolation, which our sun is emitting mainly shorter wavelengths. So our shorter wavelengths are going to be pretty much everything to the right of visible. Okay? Because visible light we know comes from the sun, thankfully. And then we have that UV ultraviolet. Which gases are absorbing on the right of this diagram? It is oxygen and ozone, B. Okay? Methane, nitrous oxide do not absorb incoming sunlight, and neither do carbon dioxide and H2O. These four are GHGs, greenhouse gases. They are absorbing the outgoing longer wavelength infrared. Okay? Same graph, different question. Which statement is true here? Is it nearly 100% of UV radiation passes through our atmosphere? Nearly 100% of visible radiation passes through the atmosphere? Or nearly 100% of visible radiation is absorbed by the atmosphere? Okay. Now look. Okay, we have 46% of you saying nearly 100% of visible radiation is passed. Let's look here at our graph. In fact, I'm just going to focus on the bottom. Whoops. Our bottom here is the total atmosphere. And I want to emphasize this graph is showing the percent of incoming radiation absorbed. Okay, so if the number here is higher, more is getting absorbed. When we look at our visible spectrum, which I'm drawing a square around, not a lot is getting absorbed. Okay, but when we think about it, visible light, the reason we see, right, it's daylight, is because our atmosphere is not absorbing visible light. Okay, so nearly 100% of visible radiation passes through the atmosphere. That is the true statement here. Okay? Questions? Comments? Clarification? Okay, you're going to see this again because this is how we understand different gases and their impact on our atmosphere. And yes, 100% of UV light is absorbed, nearly 100%. Not all. That's why we still should wear sunscreen when we're outside, because some of it is not absorbed. Yeah. Okay, so our greenhouse gases. For this class, I'm focusing on atmospheric carbon dioxide and atmospheric methane. I sometimes say atmospheric carbon. It's the same thing, right? We're talking C. The C in the methane is carbon. The C in the carbon dioxide is carbon too. Okay? We're taking carbon from one place in our Earth system and we're moving it somewhere else. Okay, so in this case, the left here, this showing the atmospheric carbon dioxide through time from 1958 until this graph is June of this year. And then on the right, this is showing methane. Okay, and so you can see methane has increased quite a bit, just like CO2. The only difference between these compounds, well, there's a few, we'll explain that as we move on in the course, but right now these are on different scales. So the right, the methane mole fraction or mixing ratio is in parts per billion. So for every billion molecules of air, there's about 1,950 molecules of methane. Okay, remember carbon dioxide on the left is parts per million. All right. So as I mentioned, water vapor is actually an important greenhouse gas. But it is so variable in time and space, meaning, one place has clouds right now, and then in 10 minutes, there might not be clouds there anymore. And clouds are made up of water droplets. And clouds can impact the planetary temperature through both an albedo and greenhouse effect, okay? And where the clouds are in the atmosphere, whether or not they're higher up in the atmosphere or lower, they have different impacts, okay? And so their height in the atmosphere matters because it has to do with their temperature and how hot they get. All right. So let's take a moment. I want you to look at this and I want you to draw in your arrows here. I'm just going to run downstairs really quick and we'll be back and we'll talk about it. So just take a minute and look at this feedback. Okay, so let's think about these. We're just going to start with a temperature change on our surface. Again, from anything, but maybe, I don't know, our orbit changed and we're closer to the sun. Okay, so our surface temperature increases. What does that do? Is that going to have a direct impact on the greenhouse effect? Or is that going to have a direct impact on the amount of atmospheric water vapor? When we think about how different things are coupled, right? Surface temperature doesn't have a direct impact on greenhouse effect. It has a direct impact on water vapor, right? Increases in evaporation, right? So if temperatures on our planet get warmer, then we'll have more atmospheric water vapor because there will be more evaporation. It's just a physical process. That does not necessarily mean there'll be more rain because all of our equilibriums shift, but it will mean there'll be more evaporation. Okay, so that's a positive coupling. And if atmospheric water vapor increases, well, the greenhouse effect will increase because water vapor does absorb a lot of infrared spectrum. Okay, and then greenhouse effect increases, that impacts the surface temperature. And so overall, this is a positive feedback because we start with an increase and then we end with an increase. Okay, so another positive feedback. I promise there'll be at least one or two negatives as we move through the course, but there's a lot of amplification naturally built into our Earth system. All right. So the Earth is not getting hotter and hotter through time naturally. Okay. And I mean a lot hotter, right? Because if we weren't emitting back out to space the heat that we were absorbing, then even on very short time frames, Earth would just get super, super hot. Okay. This is our energy balance. The amount of solar energy absorbed means the terrestrial or land, Earth energy must be emitted. It must be about the same, it must be equal, nearly equal, so that our planet isn't getting exponentially warmer. Okay, and I add the naturally here because that's not happening right now. Our atmosphere is starting to trap more of the terrestrial energy that's trying to get out to space. And so our planet is getting warmer. Okay, when we look at these diagrams, thinking of Earth's energy balance, we can get down to some of the finer scale things, right? So we have incoming solar radiation. Some of that's absorbed by Earth. Some of that's reflected by our atmosphere, right? Some of our clouds. Then we have other things happening, like we have evaporation, and we have some of that re-radiated out to space. And then we have our greenhouse gases, methane, water vapor, carbon dioxide, and they're going to trap some of that and add a little bit of heat. Now, again, I want to reiterate, the Earth before humans had greenhouse gases in the atmosphere. That allowed for Earth to have an effective temperature, an average temperature that was above freezing, which allowed Earth to have liquid water, which allowed life to grow and, humans to come around. And so the greenhouse effect is not inherently bad, but changes to it on different timescales and different rates can be bad. Okay. So right now, we're going to start to think about how we can move some of that heat via evaporation and water. How is water vapor, helping to redistribute some of the heat on our planet? All right, so what I want us to do right now is let's take a nice break. It'll probably be the only long break we get today, So let's go ahead and take like a 15-minute break, and then we're going to do some discussion on water vapor moving heat around our planet. Okay, so let's meet back at 2:45. Yeah, 2:45. Okay, welcome back. Hope you had a good little break. So we're going to talk about some concepts now that are going to lead us into understanding how our atmosphere helps with redistributing heat. So temperature and heat. Okay, so temperature, we all think we know what temperature is, but temperature is really defined by the vibration of the molecules in a substance, right? So whether that's a solid, liquid, or gas, those molecules that make up that substance are vibrating. And the rate of that vibration is actually what we call temperature. Okay, so temperature really is the average kinetic energy or motion of those molecules, right? So when the temperature is higher, warmer, those molecules are vibrating more. When the temperature is cooler, lower, those molecules are vibrating less. And we're going to compare that to heat. But first, just a real quick pause here to talk about temperature scales, right? I already introduced Kelvin a little bit, and your assignment for homework this week uses Kelvin, but you can convert between all three relatively easily. In our class, most of our assignments and discussion will be between Celsius and Kelvin. Okay, so Kelvin is the absolute temperature scale. At 0 Kelvin, that's absolute zero. Life doesn't exist at that point. Okay, and so you can see the differences between 0 degrees Celsius and Fahrenheit, 32 degrees Fahrenheit, etc. Now, heat is the total amount of energy of the molecules in your system. Okay, so heat is a little bit different because it depends on the number of molecules that you're looking at, right? It also includes the temperature. So you need to know something about the temperature of the molecules, but it's also about the number of molecules too. So a good way to think about this is a difference between a swimming pool and a boiling pot of water. Which of these has greater heat? Is it our swimming pool or our boiling water? Alrighty. So we're split evenly 50-50. When we think about heat, we oftentimes think of it solely as temperature. And that's fair. We think, oh, it's hot. There's heat, right? But again, remember, heat is a factor, or it includes the number of molecules in the system. So although our swimming pool is not boiling, let's say our swimming pool, is at like 90 degrees Fahrenheit, which is a warm pool. Our pan of water that's boiling is going to be close to 212 degrees Fahrenheit, depending upon your elevation. So obviously, the pan of boiling water has a higher temp. Those molecules are vibrating more. The kinetic energy of those molecules is higher, but the swimming pool has way more water in it. Okay, so the heat of the swimming pool would be greater because when we're thinking in this class right now, the concept of heat deals with number of molecules. And our atmosphere has a lot of molecules of water that can move heat. And so the thing here we need to think about is heat doesn't have to be super hot temperature. You can move heat energy even when temperatures are low, just simply because you're moving a lot of molecules. Okay? So again, let's think about heat transfer. So we talked about conduction, convection, and radiation. Conduction is the heat transfer molecule to molecule, and you have to touch. Okay? Here in this example, you're holding a metal pan over a fire. That metal handle is going to heat up and it will hurt you. You get burned simply because you're conducting, you're moving that heat via the touching of your skin to the metal. Convection is heat transfer by mass movement of fluid or water or air. And this is due to the fact that hotter stuff, things that have a higher temperature, are going to rise because they become less dense or more buoyant. And cool stuff sinks because cool stuff becomes, or colder, lower temperature, because it becomes more dense or less buoyant. So in our pot of water here, the molecules of water that are closer to the fire are going to heat up, they'll rise up, and they reach the top of the pan or the line of water here. Some will obviously turn to gas and evaporate, but the rest will just float to the side and get cooler and sink back down. So we get these convection currents. Radiation is the heat transfer by wave energy. So it doesn't require a medium. You don't need anything for that heat to move through. And again, all objects are radiating energy as a function of their temperature. So looking at our three types of heat transfer, which type of heat transfer explains why the fourth floor of a building is warmer than the first, even when your air conditioning is on, which is what I'm feeling right now. My office is above our garage and it is hot in here, even though it's cold downstairs. All right, so yes, here the answer is convection, right? In a building, even when you have air conditioning running, you're still going to have warmer air rising and the cooler air sinking. Okay, so convection is what causes that difference. And so remember, our atmosphere is really actually heated directly by conduction, but during the day, after conduction has had time to take place, the remaining part of the day is driven by convection. The fact that that warming air rises up, cooler air fills in where that warm air left, that cooler air gets heated and it rises, right? So we get these currents that set up. So how hot or cold does it get on Earth? Well, it gets pretty hot and pretty cold, okay? And these are the actual records, right? So, you see in the news in the recent weeks that there's been like record breaking or close to record breaking, but these are the actual records. I just recently triple checked these. The coldest temperature on our planet was measured at Vostok Station. This is in eastern Antarctica at minus 128 degrees Celsius. The hottest temperature was 134 degrees Celsius, measured in 1913 at Greenland Ranch in Death Valley. We recently came close. I think it was like 128 in Death Valley a few weeks ago, but that record was not broken. Both of these, the super cold and the super hot, these are what we call sensible heat. These are heats, right? The idea of temperature and number of molecules that we can sense. We can feel when it's cold. We can feel when it's hot. And sensible heat is changing the temperature of our objects, of our air. And when we think about moving heat or energy, we think about a flux, that idea of moving something around. Sensible heat flux is the heat transfer that changes temperature of an object. And every object, depending upon what it's made of, has a specific heat. That is the energy or the heat we need to apply to that substance to raise 1 kilogram of that substance by 1 degree Celsius. So it's standardized or normalized, 1 kilogram, 1 degree. For example, the specific heat of water is we need 1 calorie of heat per gram to raise it 1 degree C. Now you've dealt with this idea of specific heat, most likely in your life already. Imagine I have 2 spoons next to some hot water on my stove. Which spoon has the higher specific heat? Meaning it needs more energy to raise its temperature. All right. So the wooden spoon does in fact have a higher specific heat, right? Wooden utensils in your kitchen are less likely to get super hot. I'm not saying they won't, right? So you still need to practice safe cooking, right? Don't just leave it sitting there and then grab it. It can still get pretty hot, but we know the metal spoon will get hotter much faster. And that's because of that specific heat idea that metal needs less energy to raise the temperature, while the wood needs more. Okay. What about land surfaces? So imagine you're at the beach, maybe you're at Crystal Cove or Laguna Beach on a nice warm day. Which surface has a higher specific heat? Is it water, the ocean, or the sand, the beach? Okay, remember specific heat, temperature change. How much energy you have to add to change the temperature. So water does have a very high specific heat. So during the day at the beach, the water's temperature, the ocean's temperature is not going to change really. But the sand will get super hot during the day, during the sunlight hours. And then as soon as the sun goes down, that sand cools off very quickly because it has a low specific heat. It can rise or change its temperature really quickly with just a little bit of heat added. And so these differences in surface types on our planet are going to impact heating and cooling and temperature. Okay, so let's do a little practice here with some of the math. Assume the specific heat of water is 4,000 joules, another energy unit, per kilogram degree C. Okay, so you need to add 4,000 joules per kilogram to raise water's temperature 1 degree. If our starting water temperature is 14 degrees Celsius and our water receives 12,000 joules per kilogram, what's the final temperature of that water going to be? All right, here we go. So 2 steps to this type of question. The first is, well, we know the total energy we received was 12,000 joules per kilogram, and we know our specific heat of our substance. So we can then find the temperature change. Okay, so that's 12,000 joules per kilogram divided by 4,000 joules kilogram degree C, that means we're going to get a 3 degree C temperature change. And we started with 14. Okay? So by the end of the day, our surface would be 17 degrees C. Now, the implications of specific heat on global climate. When we look at this image, this shows us the day minus night temperature for just 1 month in 1 year. Orange colors means it's much hotter during the day. The blue colors means there's no change, or the light blue, no change from day to night, and the darker blue is a little bit cooler during the day. What you'll notice here is that our land masses, our continents, they see a big temperature difference. They are much hotter during the day than the ocean. And that's because of their specific heat. They heat up and cool down much faster than our oceans. Our oceans have this like moderating effect on climate because you have to add so much heat to the ocean for it to change its temperature. Okay, I'm going to repeat that. You have to add so much heat to the ocean for it to change its temperature because it's made of water, and water has a high specific heat. Okay? It has a high heat capacity. It can absorb or lose a large amount of heat without actually changing its temperature very much. And so this is going to come up at the end of the semester or summer session when we talk about observed changes to our climate. The ocean is getting warmer, not very fast, but it is absorbing a lot of excess heat in our planet. So sensible heat, we can measure it, we can sense it. We also have a different type of heat. Well, yes, because the 1.5 to 2 degree temperature is it's what we're measuring in the atmosphere. The ocean won't be nearly as hot. It won't see as much change in temperature, but it's absorbing a lot of heat, which can do other things to the ocean ecosystems. So the next type of heat is latent heat, and latent heat is hidden. It doesn't change the temperature. Rather, it's changing the phase of the object. In this case, we're going to talk about water. So when we change phase between solid, liquid, and gas, that requires an input of energy to make that change. So in this latent heat, the temperature is not changing. Rather, we're just using energy to change phase. Why is that? Because water is made up of these beautiful and interesting hydrogen bonds. And these hydrogen bonds require energy to break them or add them or make them. Break them or make them, you have to add a lot of energy. And so when we're going from solid to liquid to gaseous water, we have to add a lot of heat. And so here's kind of our thought process to go from solid or ice to go to liquid. You need to add energy. That's what we call melting. And that energy usually comes from the environment or the air surrounding that ice. The same is true for evaporation. You have to add energy, and that is usually coming from the environment, heat coming from the environment. And the opposite is true when you start condensing. You have to release some of the heat, and you release that back to the environment, like the atmosphere, and then the same with freezing. Now, I like to visualize numbers. And so this graph here is showing on the x-axis the number of calories needed, and on the vertical axis is the temperature. So if we're going from minus 40 up to 0 degrees C, we are measuring a sensible heat change. We're adding heat, and we can measure the temperature change. But if we want to go from ice to liquid at 0 degrees Celsius, you cannot do that unless you add 80 calories per gram. That's called the latent heat of melting or fusion. And so without that extra 80 calories, you will stay as ice even at 0 degrees C. So a common misconception is that right at that temperature threshold, you change states. That is not true. Without that extra energy, you can technically be a liquid at 100 degrees C, which is boiling, until you get that extra heat, that latent heat of vaporization. Okay, so you have to add this large amount of heat to change from liquid to vapor, or you have to take it away to go from vapor to liquid. Okay, let's practice. How many calories does it take to evaporate 1 gram of water? Okay, so evaporation means we're going from liquid to gas. So we're going, in this case, from location C to D. We need 540 calories to do that. It's a lot of calories. How many calories does it take to melt 1 gram of water? Well, that's the latent heat of melting, 80 calories per gram. Now, how many calories does it take to increase temperature of 1 gram of water from 10 degrees C to 90 degrees C? Well, this is a sensible heat change. We're actually measuring the temperature change. We can sense it. So this is going to use the specific heat of water value, which is 1 calorie per gram degree C. So my delta T, or delta means change, my change in temperature is 90 minus 10, which would be 80 degrees. And I know I need 1 calorie per gram per degree C. So times 1 cal per gram degree C, and we find out that we need 80 calories. So it takes the same amount of energy to raise 1 gram of water's temperature 80 degrees Celsius as it does to melt 1 gram of water. Now, last one, how many calories of heat is needed if I'm going to take my temperature of water from 60 degrees C to 120 degrees C and have evaporation occur at the 100 degree threshold? Okay, so 2 steps. First is the latent heat. Latent heat with the evaporation process, 1 gram at 540 calories per gram. That's a 540 calorie process alone. And then our sensible heat process is that 60 degree C change at 1 calorie per gram. And that is another 60 calories. So the total in this case is 600 calories. Now, when we look at these numbers, we can see what is taking the most energy. What requires the most heat? What process in this figure and in these examples requires the most heat to accomplish? Is it melting? Yeah. It's not the changing temperature. It's not the sensible heat change. It's the vaporization or the evaporation. So evaporating, and then the opposite of evaporation, condensating, water on our planet requires a lot of heat. And our planet is 70% water by surface area. So we can move a lot of heat by that evaporation process. Why do you put ice cubes in your drink to cool it down? All right. The answer here is the fact that ice is absorbing heat from the environment. And in this case, the environment that that ice is in your drink, the liquid of your drink. So it takes the heat from the drink in order to change phase. And so it cools your drink down. It's pretty cool. And we use this idea of latent heat of vaporization. Many mammals, like you and I, we rely on latent heat of vaporization to reduce our body heat. When we sweat, right, the little beads of water come to our surface of our skin. That water evaporates. The evaporation process requires heat. Where does the heat come from? It comes from our body, and it helps cool us down. It's a way that we can release more heat. So on our planet, the large latent heat exchanges during evaporation and condensation are transferring a huge amount of energy around our planet. And I mean huge. We have a lot of evaporation happening in our tropics where it's warm, where we get a surplus of incoming sunlight, right? On Tuesday, we saw that the equator's always getting sunlight, even, our winter, because it doesn't actually really experience much seasonal change. So there's always a lot of evaporating happening in the equator, and that can transfer heat to what we call precipitation latitudes, the mid latitudes or the polar regions. So we're taking extra heat from the tropics, moving it to a place that has less heat, the poles. And this is what we can see if we look at our planetary energy balance by latitude. Okay, so here is 0 degrees. So the equator on the x-axis is in the middle, the North Pole, 90 degrees on the left, and our South Pole, 90 degrees on the right. The blue line is showing the amount of incoming sunlight each latitude gets. And the red line shows the amount of outgoing heat from the Earth, long wave. What we see is that we are sending more heat back to space at our high latitudes, at our polar regions, than those places receive. And the only way that is possible is if our atmosphere and our oceans are transferring extra heat from the equator to those places. Okay, so important to note that the amount of energy we absorb at each latitude does not equal the amount our planet is emitting at each latitude. And that's because of our atmosphere and our oceans. Very important in keeping the planet, our climate system, the way it is. This introduces something in terms of atmospheric pressure. Pressure, as I mentioned earlier, is force per area. And in atmospheric science, there are so many different units or standards of pressure. We can have PSI, pounds per square inch, millimeters of mercury, torr, pascals. It can be confusing. For this class, we're going to look at millibars, which is also the same as a hectopascal. But if you take all of the air above our head and you're at sea level, you would have about 1,013 millibars of pressure from the atmosphere above your head. That's the average. Looking at our equation for pressure, force over area, what could happen to pressure if we increase the area? Okay, so in our equation, if you increase the number on the bottom, it would make the pressure smaller, right? So for example, let's say we start with force is 1 and our area is 1. Just as an easy example, if we increase the area to 2, that becomes 1 over 2, which is 50% or half. Okay, so when you increase the area, you're going to decrease the pressure. Now, the relationship between pressure and temperature is sometimes expressed as the ideal gas law. I don't want you to get too hung up on this equation. Rather, I just want us to understand that when you change the volume, V, that impacts pressure, P, and there's also an impact on temperature, right? All of these things go together. Pressure, density, temperature, they all have a relationship, and this relationship is this ideal gas law. For this class, we're going to very generalize it in that warmer air, temperature, will be more buoyant and will rise up. That's why during the day, the surface gets warm, the air rises up. This is why hot air balloons work, okay? I took this picture when I was in France earlier this summer outside of our Airbnb. It was amazing. You can hear, they turn the heat on in these balloons, they rise up. When they're ready to go down, they turn the heat off, they actually can let some air out, helps them cool down and sink. Warm air rises, cold air sinks. And winds on our planet, winds are moving air. When we think it's windy outside, that's air moving. And winds are always moving from areas of higher pressure to areas of lower pressure. And that's true of everything, high to low. I always joke my bank account every month goes from high to low. High pressure, low pressure, that's how our winds are going to move on our planet. Now, pressure is going to be changed, can be impacted by heating, right? Here's our convection currents. When we have warm air or air warming and rising, what happens is that air is moving away from the surface, and that creates what we would consider lower pressure. Molecules of air have moved away, so now there's lower pressure there. And as I just mentioned, air always moves from higher to lower. So therefore, air wants to come in to fill in that lower pressure. And because our surface of the Earth is unequally heated, that is driving our surface winds and our atmospheric circulations because it is always hot at our equator. And that means the air above the equator, at the equator surface, is heating and it's rising off the surface, creating lower pressure rather continuously along the surface, lower atmospheric pressure. Okay, what I want us to do now is I want you We're going to watch this video for like 45 seconds or so. And I want you to make note of what you see in our atmospheric circulation. This is using satellite data. They have colorized some of the winds and the wind patterns so you can see them better. While you're watching, make note of what you see. Are the winds on our planet all moving in the same direction? Also, some of the colors here are clouds. Are there areas where it's kind of persistently cloudy? Like here, for example, these reds are tall clouds, very thick clouds. What do you notice? Okay. Yep. Seems to be a prevailing or a dominant wind direction depending on latitude. The oceans, there's quite a bit of cloudy. Yeah, there's quite a bit of cloudy near the middle, near our equator. And our winds have a certain direction that they flow. Well, we're going to learn why. And it's actually a pretty simple model to explain why. Now, if we just think about where our planet is generally warmer and where it's generally cooler, we will get a wind setup. Okay, so as I mentioned, our equator is usually pretty hot all the time. And so therefore, the air at the equator is rising off the surface, away from the surface towards the top of the atmosphere. And you should pause here to emphasize this is looking and interpreting the Earth in 3 dimensions, right? The atmosphere, when I draw an arrow off the surface here, I'm referencing it's moving away from the surface towards the top of our atmosphere. So the hot air rises. It can't go on forever. It's going to reach the top of the atmosphere and it spreads out in both directions. Now it's away from the heat source. It's going to cool down and sink. We know that when air rises at the surface, it creates lower pressure. We're taking air and moving it away. So the force per area gets smaller or lower, low pressure. Now, when you have air sinking down and hitting the surface, that creates higher pressure. Now we have more molecules of air. So we get higher pressure at our polar regions and lower pressure at the equator. And that would mean, based on what I told you, that winds flow from high to low pressure. At Earth's surface, we would have winds blowing directly from the poles to the equator. So on a non-rotating planet, winds would flow straight towards the equator along the surface from both of our poles. But I told you yesterday, and you know this, our Earth is rotating. So for example, here is what's going on right now at the surface. And I'm just using Hawaii here because I mentioned there was this hurricane off the coast of Hawaii driving those catastrophic fires. You can see that the flow is not directly from the poles to the equator. You can come over land here and we can see that it's much different than just that simple model. And that is because our Earth is rotating. Okay, and with that rotation comes this force or effect known as the Coriolis effect. It's not a real force like gravity is, but it is an apparent force due to the fact that Earth is rotating. And because Earth is rotating, it makes it look like objects that are not connected to Earth's surface, they get deflected. The best way to explain this is to show a video. So I'm going to show you this video about the Coriolis effect.
What's going on here? Every time I throw the ball straight, it seems to bend to the side. No matter what I throw, no matter how straight I throw it, the ball seems to be curving. Maybe it has something to do with this. That whole time I was spinning, which is why it looks like I'm about to puke. That curve is created by the Coriolis effect. You may have heard that it makes water in the bathtub spiral down the drain a certain way, or that it determines the way a toilet flushes. That's actually wrong. Those are not caused by the Coriolis effect. But the Coriolis effect is what makes hurricanes spin, and it's the reason why Jupiter's Great Red Spot is spinning the way that it is. So what is the Coriolis effect? Well, it's what happens when objects moving in a straight line appear to curve because you are rotating. And it affects all kinds of things. It bends the paths of missiles and sniper shots. But how does it work, and how does it create hurricanes? Right now, it seems like the ball's curving, but let's take a look at what's really happening. My friends and I put together this little experiment using a sort of spinning seesaw. Here, the camera's standing still. It's just hanging from the ceiling. And watch what happens. From the moment the ball leaves my hand, it's just going straight. Let's watch that again, frame by frame. Keep your eye on the ball. You can see it travels in a perfectly straight line. But what if you're spinning with the seesaw? Look at what happens when you rotate the footage so the seesaw stays sideways and everything moves around it. Now let's follow the path of the ball again, but from this new perspective. The trajectory looks completely different. Now let's watch this one frame by frame. From this rotating perspective, it totally looks like the ball is curving. That's crazy because you already saw that exact same throw. Watch it again on the left. The ball is going straight, but on the right, when you're rotating with the seesaw, the ball really looks like it's curving. You might be thinking, why should I care? I don't spend a lot of time on a spinning seesaw or on a merry-go-round. But you kind of are on a merry-go-round. The Earth is constantly spinning. Have you ever seen someone in a movie making fine adjustments on their gun? Well, one effect they're correcting for is the Coriolis effect. The longest sniper shot, which was over 3,000 yards, would have had to correct for a 1-foot deviation due to the Coriolis effect. So how does the Coriolis effect create hurricanes? Hurricanes form when air rushes from all directions into a low pressure region. So imagine there's a low pressure region between the two of us. Air is going to rush toward the center. Let's see what that looks like from space, from our camera that's hanging from the ceiling. It's not spinning, so the air, or in this case the balls, are clearly going in a straight line. But if you're rotating with the Earth, or with the seesaw, you'll see the air bend to the right. In the northern hemisphere, this creates hurricanes with counterclockwise spirals. In the southern hemisphere, it does the opposite. It creates hurricanes with clockwise spirals. This storm on Jupiter, which is actually bigger than the Earth itself, has been spinning for at least 200 years, largely due to the Coriolis effect. So when you're in a rotating frame, the Coriolis effect seems to exert a very real force on objects. But there is no force. What you observe is just a result of your perspective. And you might be wondering, if this is simply a product of...
Okay, so that is the Coriolis effect, Coriolis force, and it impacts our winds because the air, our atmosphere, is not connected to the Earth. And so as the Earth is spinning beneath the air, it can make the air appear to be deflected. Okay, so our rotating planet, our Earth is a sphere with a wider equator, a wider belly. Okay, the circumference at the equator is about 40,000 kilometers, which means that at the equator, our Earth surface, equator, is moving at about 1,000 miles per hour. But at the Arctic Circle, the speed is less because the circumference at the top of our sphere is smaller. Okay, and so this means that during the day, if you're near the equator, you're actually spinning faster than somebody near Alaska, for example. Okay, so Coriolis is actually maximized at the equator, or excuse me, not at the equator, at the poles. You have to spin faster because you're not moving as fast. And so to complete the day at the same rate, you'd have to spin faster. And so there's no Coriolis actually on the equator itself. There's no spinning effect. It is it gets larger as you move away from the equator. So maximum Coriolis is at the poles. There's no Coriolis at the equator. So the strength of this Coriolis effect depends on the latitude. Where are you? It depends on the rotation of the planet. So as mentioned, Jupiter is spinning much faster than Earth. And so its impact, the Coriolis, is much greater. It also depends on how fast the moving object is. So you and I, when we're driving our cars, one, we're connected to the Earth by gravity, so that doesn't impact us. And also, you know, airplanes, they're moving pretty fast. And so they do have to correct for this Coriolis effect. The fact that you're in the air, but the Earth is spinning beneath you, okay? The Coriolis effect deflects to the right in the northern hemisphere and to the left in the southern hemisphere. And this deflection occurs along the path of motion. So you have to think, where am I starting? Where am I going? And the deflection is to the right in the northern hemisphere. So let's think about Iron Man here. Iron Man tries to go from New York down to Miami at the southern part of Florida, and he doesn't take into account Coriolis in his flight plan. So where is he going to end up? All right. So, as mentioned, it's on the trajectory. You have to think about where you're going. So in this case, Iron Man is trying to go from up here down south to Florida. But as he's flying, the Earth is rotating beneath him. So this area is rotating. Florida is moving away from him. And because he didn't take into account that rotation, he's going to end up at location C. He's trying for B, but he gets deflected to the right of his motion. If you don't understand, turn upside down and look. He's moving down, and in the direction of his motion, he gets deflected to the right. So if he wanted to land at B, he should aim for A. And this is what pilots do. In their calculations in their cockpit, they put A into the system. And as they're flying in the air, the Earth is rotating beneath the plane, and then they'll land at B. So this impacts our winds. So on Earth, right, we know that we're going to have our winds blowing from high to low pressure. And so here, imagine these are areas on the left here is an area of higher pressure. So the winds want to flow outward. basically in all directions, because anywhere around it will be lower pressure. So the winds want to go from high to low. But we have the Coriolis effect. And if we're in the northern hemisphere, that's going to cause these winds to get deflected to the right, to the right, to the right, and to the right. And we can do the same thing over here with low pressure. In a lower pressure system on Earth's surface, air is going to come from higher pressure in all directions. Okay, so air is coming from higher going to lower. And in this case, again, we still have the Coriolis and that deflection. And we're in the northern hemisphere, so it's to the right of motion, to the right, to the right, and to the right. And so you can see here that at low pressures, winds are going to be moving counter clockwise. And on the high pressure, they'll move clockwise, meaning clockwise, the hands of the clock, going from 12 noon all the way back to 12. They're moving in that direction. Counterclockwise means they're moving the opposite direction. And so this puts a kind of switch, a little change up on how the surface winds are going to flow on our planet. So if we look at our planet near the equator, where it's super, super warm, we create that low pressure, right? And the air is rising up off the surface. It reaches the top of the atmosphere. It can't go any further, and it spreads out in both directions, north and south of the equator. At some distance from the equator, two things happen. One, the air starts to get super cold and wants to sink. And also we have the Coriolis. It starts to deflect the airflow. And in the north, that deflection is to the right, which just so happens to be down, back to Earth's surface. And in the southern hemisphere, it's to the left, which also happens to be down. And so we call this the Hadley cell. Around 0 degrees at the equator, air is rising off Earth's surface, and around 30 degrees, both north and about 30 degrees south, air is sinking from higher up in the atmosphere down to the surface. And this Hadley cell is called a thermally direct cell, convection cell. It is driven by thermal energy, heat. Air is rising in the warm area along the equator, and it is sinking over a colder area. Relative, right? It doesn't have to be cold, it just has to be colder. Okay? The polar cells are a very similar thermally direct cell where we have very cold air sinking at the poles and warmer air at around 60 degrees north and 60 degrees south, rising off Earth's surface. It's called the polar cell because it's near the poles. It's the same idea as the Hadley cell. Okay, so just for time, I'm just going to tell you, right? The polar cells are a thermally direct cell. That circulation is driven by the temperature differences between the poles and about 60 degrees north, that 30-degree latitude difference. Now, in between, we have another cell, and that's the Ferrel cell. It fills in the gaps, basically, right? So if you have air sinking at 30 degrees and rising at 60, you create another convection or another current. We call that the Ferrel cell. And the Ferrel cell is thermally indirect, okay? it's not actually developed by temperature difference. Rather, it's there because there's turning wheels on either side of it. Okay, so we have our Hadley cell here near the equator and our polar cell over here near the pole. Those are turning, and so you just have another circulation in the middle. And that's our ferrule cell. So it's not really driven by temperature, it's thermally indirect, and it exists because of the wind circulations of the other two cells. Okay? This leads us to this 3-cell model. The fact that our Earth is rotating, we don't just have simple circulation. We have what we call a 3-cell circulation. And I'm going to leave that. You have this one on your slides, but I'm going to talk through and make my own so you can understand how our winds blow. So we have 0 degrees, 30 degrees, 60 degrees, and 90 degrees. We already say it's really hot at our equator. And because of that, air is rising off the surface high up. It reaches a point, the top of the atmosphere, it spreads out in both directions, and eventually it starts to sink back to Earth's surface. That happens around 30 degrees north or south. And when you have air sinking, it creates higher pressure. And so we create these bands of higher pressure around 30 degrees north or south. Okay, we also know that we have sinking air at the poles, rising up again around 60 degrees north, and then we can fill in that ferrule cell. And where air is rising off the surface, it creates a lower pressure. So we still have lower pressure here around the 60-degree mark. Okay, fine. What does this do with surface winds? Well, we have these areas of high and low pressure at the surface, which means we're going to induce surface wind. Let's start here in the northern hemisphere. Air wants to go from high to low, gets deflected to the right. Air wants to go from high at 30 degrees to lower pressure at 0 degrees, gets deflected to the right, high to low. So the winds in this belt, this latitude, flow from the east to the west. We call these easterlies. Now I'm going to move to the southern hemisphere. I'm going to do the high pressure at 30 degrees south to low. Air wants to go from high to low, but we're in the south, it gets deflected to the left. High to low gets deflected to the left. High to low, deflected to the left. These are also easterlies. In the 30 north to 60 north area, winds want to go from high to low, but get deflected to the right. Get deflected to the right. These are called westerlies, blowing from the west to the east. And at our pole, at our north pole, we have high pressure trying to go to low, but it's going to get deflected to the right. And so we get easterlies again. All of this was set up by temperature differences. And the fact that temperature differences induce pressure differences and that winds move from high to low pressure. Okay, so you have it drawn out here on this slide. But if we think about it, we notice in our satellite imagery that our winds are moving in different directions. So this model actually explains why our surface winds move the way they do. So our observations, we see one thing we noted was that cloudiness near the equator. That's called the intertropical convergence zone. Intertropics, two tropics coming together, convergence coming together. When air is coming together, it rises. And we're going to learn you get clouds. So lots of clouds there. Where there's clouds, there's sometimes rain. Our deserts are located a little bit away from the equator. Okay, so intertropical convergence zone, air is coming together at the equator. It's being forced upwards. And when it is forced upwards, it cools. Sometimes you can get condensation and sometimes you get rain. And this is a semi-permanent feature of the planet. Anytime you take a satellite picture, you will see this band of cloudiness. Low pressure near the equator causes pretty constant rain. Low pressure leads to rain, cloudiness and rain. High pressure, on the other hand, leads to the opposite. So where would you expect deserts to be located based on this three-cell model? If low means rain, low pressure means rain, high pressure would mean the opposite of rain, sunny, dry. All right. So yes, near that 30-degree mark, where the air is coming down from higher in the atmosphere and then hitting our surface and creating high pressures. So about 30 north and 30 south, it's not perfect, but around those, plus or minus a few degrees latitude, that's where we find our great deserts on our planet. The Sahara, Patagonian, the Great Sandy Desert in North America. We have our deserts here. So the three-cell conceptual model, does it match reality? It can explain some of the features we see, like the intertropical convergence zone, our wind directions, and our desert distributions. What it doesn't explain is our upper atmosphere, what's happening high above our heads, like the jet stream, for example. And it doesn't take into account land. It doesn't know how much land there is in each hemisphere. It doesn't know about the heating and cooling differences between the land, which will set up pressure differences too. So on Tuesday, we're going to complete our understanding of atmospheric circulation by talking about these factors that we cannot explain with our three-cell model. All right, so that's all I have for today. Finished right on time. So quiz 1 is due Monday. So is your homework 1. I highly, highly suggest you watch the videos that I have linked to help you with some of that Excel. I might even make another one and post it this weekend. I'll see what time I have. Also, if you have questions, please look at that sooner rather than later. And send me your questions. And what else am I missing? Your daily check-in. Make sure you don't forget to do your check-in after lecture today. Otherwise, I'll see you all on Tuesday. Have a great weekend. Bye.